to wake up early enough. So yeah, welcome to the second day of WoLA. And we're delighted to have Guy Rothblum from Apple telling us about interactive proofs. So I'm guessing this is very fitting if the talk is interactive. So if you have questions.
I mean, usually we want non-interactive, right? Eliminating interaction is a positive, but in the talk, preferably, interaction is good.
And yeah, I won't take more of the time, so please, the floor is yours.
Perfect. Thank you. So thanks everyone for getting up at this. For me, it's fine because I'm jet lagged, but the inhumane time. And I want to talk about a line of work. I'll focus on one specific recent work towards the end of the talk, but I want to tell you kind of about a line of work or a body of work aimed at verifying data science computations using proof systems from computer science. So is the red visible? So this is the official Apple slide template that I was asked to use. So apologies for the colors, but this is what we have. Okay. So we know that data science, machine learning, and statistics are transforming science, society, industry. And there's a lot of promise in these analyses that take valuable data sets and glean insights from them. But there are also risks or perils that we need to think about as we're viewing this transformation. And I won't talk today about privacy or about fairness. The main thing I wanted to talk about in the talk today is the issue of if we have more and more high-stakes computations, data science computations that are really affecting the world, that are informing decisions like whether people go to jail or not, whether there's this recent, like, really shocking story about the risk tool in Spain used for assessing the risk of for women with abusive partners, the risk of being harmed by the partner. So anyway, there are really high-stakes decisions that are being informed and made based on algorithms run on data. And how do we know that what the algorithm is telling us to do is correct? And there are many aspects of this question. I want to talk about some of them today. So to think about that, I want us to recall this, and the connection to WoLA and sublinear algorithms will be very clear throughout the talk. So if that's bothering you now, don't worry about it. It'll be in scope. Okay, so this is a basic machine learning or statistics pipeline where we have some underlying distribution on valuable data, maybe patients with a disease. We draw samples from the underlying distribution. Maybe it's voters in an election. We draw samples, collect this valuable data set. We run a sophisticated algorithm to analyze it, and we arrive at some useful conclusions, maybe statistics about the population, maybe it's language, language data, and we're training a language model, or maybe we are training some loss minimizing predictor that will predict whether a certain person will have heart disease or whether someone will recidivate if we release them on bail. And as we said, there are very high stakes decisions or consequences to the outputs of these computations. So how do we know, that's the question today, that the conclusions that were arrived at are correct? Okay. And I want to, I want to separate between two different concerns, one of which I won't talk about in the talk today, and the other I will focus on. So one is, it could be that the data set is fine, but we don't know, or we don't trust that the algorithm was run correctly. Okay, that's one very classic problem we deal with in cryptography and complexity theory. Usually people talk about it as delegating computation. That's not what I want to talk about today. The new problem, the more challenging problem I want to talk about is how do we know whether we should trust this data set or not? It's supposed to be, for example, in a basic statistical setting, this is supposed to be IID samples from an underlying distribution. How do I know whether it was, was there some bias in the selection? Was someone malicious in the selection? What do we do if we can't trust this data set that was gathered? How can we gain confidence in the results? Or how can we be confident that the results of the analysis are correct? So that brings me to the subject of the talk today, which is sort of verifiable data science. We want to verify complex claims pertaining to data analyses that were run on data that we don't necessarily trust even the data that were supposedly sampled from the underlying distribution or that were arrived at. But we still want to verify that the claim is correct or approximately correct. So how can we do that? And the way I want to do that in the talk today is using a proof system. So a probabilistic proof system from theoretical computer science literature, and we'll talk a lot about what I mean when I say proof system. But proof system could be, what's a proof? For me in the talk today, a proof is something that's easy to verify. Okay, so the main point is that we want some sort of a system where verifying that the results of the analysis are correct is easier than running the analysis yourself. Okay, so of course I could just go, and if I want to verify that the results of the analysis are correct, I could by myself go and sample a new data set using IID samples from the underlying distribution. I could run the expensive computation myself. I could arrive at some conclusions, and I could see whether they're approximately the same as what was claimed. That's not a proof system. Okay, it is verification, but it's not a proof system. Proof system is something where verifying is easier than performing the analysis by yourself. And I don't just, I mean, I won't focus on it today, but I have to mention it. I just don't just want to focus on verifying the result efficiently. I also want that generating the proof, convincing, should be feasible. Okay, so I want what's known as a doubly efficient proof system. Generating the proof should not be too costly. And I'll mention, it won't be the focus of the talk today, but I'll mention it. Okay. So that's the approach I want to take in verifying the results of these statistical computations or data science computations. Okay, so I want to verify something like, is this hypothesis that was arrived at a loss minimizer with respect to the true underlying distribution? Are the statistics that are being claimed approximately correct with respect to the underlying distribution? We'll talk about general properties in a second. And of course, how can we do that? If we don't have any access to the real distribution, there's no way to do that, right? I don't trust this data set. So as far as I know, the data is just totally made up. I can't verify correctness without any access to the underlying distribution. Okay, so we need some access to the truth. Okay, and the main point when I talk about efficient verification today is that you talk about different notions of efficiency. The one I want to talk about today is that we can verify using less data than would be needed in order to run the analysis ourselves. Okay, so now sample complexity or access to the underlying data is becoming one of the critical resources we talk about when we talk about efficient verification. So I want proof systems with efficient verification in terms of access to the underlying data. Let me just mention that you could talk about many different kinds of efficiency with respect to the underlying data. So maybe you want efficiency in terms of it's enough to have some noisy access to the data. Okay, so that you couldn't do the analysis yourself, given a certain level of noise, but maybe you can verify. You can talk about things like maybe you can verify using only samples, an analysis that would require Oracle queries to some underlying labeled data. So we can talk about different notions of efficient verification. For the talk today, I really want to focus on sample complexity as a measure. So I want fewer samples for verification than would be needed in order to run the analysis. And now we can think about what kinds of computations can we verify while thinking about this resource. Okay, what kinds of things can we verify using less data than we would need to run the computation? And I think it's a very exciting, very big question. I'll focus on mainly on one setting, but I'll mention two settings in the talk today. Before going into that, while we're still at this very high level, I kind of want to tell you that I think this is a worthwhile pursuit, because we know that studying proof systems, studying kind of the question of which kinds of computations can be verified efficiently and how, okay, what's a proof system, and what are the resources, and what can we say? It's really central to theoretical computer science at large. There's been a lot of research focusing on classical resources like time, the time to verify versus the time to decide a problem. And that's the P versus NP question. And studying general notions of proof systems, starting with Shafi and Silvio Micali and Charlie Rakoff's work on interactive proof systems. But the whole kind of zoo of probabilistic proof systems that have been studied since then has really transformed our understanding of computation and of cryptography. And the hope is that studying these questions now in terms of the new resource, when we're talking about data science, in terms of access to the data, can also lead us to similarly deep insights in that regime. Okay, so that was kind of my high-level pitch. More concretely for the talk today, I want to revisit the notion of interactive proofs for this setting for data science. So what we have is an underlying distribution. Okay, that'll be the cloud, this beautiful Apple-approved cloud for the talk throughout the talk today. We have some analysis that's been run, so many samples have been drawn, and by this untrusted party, it's making a claim about the underlying distribution. Okay, maybe it found a loss minimizer, maybe it's claiming some other property of the underlying distribution. We want a proof that the claim is approximately correct. So we're going to deal, for this crowd, approximate correctness should be very familiar and comfortable, but let me just say that we don't, there are always going to be sampling effects, right, when you draw samples from an underlying distribution. So we don't want and we don't care about exact correctness. We want to verify some notion of approximate correctness of the claim being made about the underlying distribution. And the way we do that is using this verifier can verify the claim using an interactive protocol. So it can draw a few samples from the underlying distribution, okay, ideally many fewer than would be needed to run the analysis. And then we can have a challenge response interactive protocol with the untrusted prover. And at the end, the verifier should accept or reject the claim. Okay. And to repeat myself, the main point about efficient verification is we want fewer samples than would be needed to run the analysis, but we care about all the different measures of efficiency. So we want really efficient verification, minimal interaction, minimal communication complexity, minimum running time of the verifier. We want very efficient proof systems. Okay, so having said that we want to minimize interaction, I think it's a good point for a question. Yeah.
So is there like a distinction between private and public randomness, or do you care? Or
wow, it's a great question. So we always care about private versus public randomness. This setting is very different from the classical setting. So we don't have results like Goldwasser and Sipser. Private coin protocols cannot, in general, be transformed into public coin ones, and I think we even have separations for some specific tasks. We have separations. But of course, we do care. So we would much rather have a public coin protocol than a private coin protocol. And Tal Hellman, who's sitting there, has some recent work showing that for some of the problems I'll talk about today, I will be presenting private coin protocols, but there are non-trivial public coin protocols as well. Yeah.
Yeah. So about the setting here, how do you envision that distribution D to be available? Is it like the verifier has a data set and like releases a few data points to the prover has that and releases a few data points to the verifier, or is there like a general sampling way, but somehow the verifier has limited access to it? What would be a good use
so I
case?
think so definitely we don't trust the prover to give us samples because it can be making everything up. But think about, there's a medical study, for example, and you I don't know, about cancer patients, and you need a certain number of samples to run an analysis to understand the causes of cancer or predict. And you want to be able to verify the results of the analysis. To verify them, you will have to go and sample patients from this distribution, but hopefully many, many, many fewer than you would need to run the analysis. In some sense, I mean, I think it's very interesting to think about other models, but you need some access to the truth, right? The verifier needs some access to the truth. Okay, so yeah.
So instead of having an untrusted prover, have you considered a setting where you could have like some possibly erroneous advice? Maybe you could still get away with like a smaller sample complexity.
So erroneous advice, what do you mean, that it's like non-interactive, or do you mean that it's not malicious or something like that?
It could be good, it could be bad, but maybe you could parameterize it by like the quality of the device.
Yeah, so I don't know. That's a good question. Like maybe you have some sort of erroneous, you have some bound on the amount of errors that the untrusted party or advice is going to introduce. We haven't really considered that, but there could be interesting questions to ask there. Okay, so just to continue on the high level, I think this is super exciting, because imagine if we could really solve these problems, and we could live in a world where every data analysis comes with an efficiently verifiable proof, public coin, non-interactive, you just need 5 samples from the underlying distribution and you can verify. That's a world that would be very exciting to live in, right? Okay, so one thing you could do is you could send out all of your data science, computation, and data analyses, farm them out to untrusted parties, and they would tell you everything you want to know about the universe and also give you a proof that they did the analysis correctly. And it's very hard. I mean, these are real world problems. Hospitals are outsourcing their data science tasks to these companies that, at a price will do data analyses for them. And how do you know they actually collected any data? They did expensive computations. These are real questions we want to solve. We're talking about verifying the results of scientific publications. So we know there's a replication crisis in science, and many results don't replicate. So people publish papers, and then other people try to verify the results. And the state of the art, or like the classical way to verify the results of a scientific experiment, are to see whether it replicates a scientific finding, to see if it replicates in other labs. And like we said before, I think that's a way of verifying that the results are correct. But as a proof system, it's a very dumb proof system. You sort of have to go through all of the costs of rerunning the experiment, whether that's collecting a cohort of patients, or if it's in physics, you need to like run your particle accelerator and create many particles. Imagine if we could live in a world where people who submit their new findings to journals also submit a proof, and the proof is easy to verify. That's a way to at least mitigate the replication crisis in science. Auditing, making it easier to detect and reject fake facts. I think we're living in a world where there's a lot of information, there's a lot of supposed insights about these informations being sold to us or told to us, and it would be really nice, or I think it's really important to be able to have a theory and a collection of tools that allow us to check these kinds of claims very efficiently and quickly. Okay, I'm not going to solve all of these problems in the talk today, but it's motivation. Okay, so I want to give you two examples. The first one will be very quick, and then the second one I'll go into in more detail of the kinds of analyses we can verify for which we have proof systems. So the first one is for agnostic learning task. This is work with Jonathan Schaffer, who was a student here, and Amir Yudayov, and there's a really nice recent work as well of Gur et al. So here we're thinking about an underlying distribution on labeled examples. Okay, so we have think of these as individuals. Every individual has a collection of features and a label. Maybe it's someone who was who was released on bail and whether they committed a crime while they were out. And you want to train a predictor to know the labels of, you're given a collection, a training set of samples from this underlying distribution, and you want to train a predictor to predict the labels of new examples that you haven't seen in your training set. Okay? And in agnostic learning, what you want to do is you want to find a hypothesis for labeling new examples that has minimal loss within some benchmark class H of hypotheses. I'm assuming this is sort of familiar to people in the audience, but stop me if it's not. Okay, so now we have some prover, and he claims that he has run an agnostic learning algorithm. He found a hypothesis that minimizes the loss within some benchmark class H. Okay. So of course, if he claims suppose he comes and he says, here I found a hypothesis and it has 99% accuracy. Okay, I can verify that by taking a few samples from the underlying distribution and using a Chernoff bound. If he claims it has 80% accuracy, I can also verify that the 80%, it's just a Chernoff bound. I draw a few samples from the underlying distribution and I verify. But how do I know if it's minimal? Okay, so he says 80% is really good and minimal in the class. It's a difficult task. How do I know whether it's minimal? That's the difficult thing to verify. So what we want is a proof system, an interactive proof system, where if the prover is cheating, if there is some H star in the class that has much better loss, then the verifier rejects with high probability. Okay. So that's the task. I don't want to tell you much more about it, just to tell you that you can do non-trivial things. So we show a natural class where there's a proof system where you can verify using square root of the VC dimension samples. So learning information theoretically, to learn a loss minimizer, you need VC dimension samples. And here we have an efficient verification that verifies using square root samples. So that's a separation. Right here, verification is provably easier in terms of sample complexity than learning would be. There's a really interesting open question of characterizing the verification complexity of hypothesis classes. So we know that the VC dimension characterizes the sample complexity of agnostic learning generally, at least information theoretically. And we don't know how to characterize. We know that for some classes, natural classes, we can get a savings. For others, we can't. And characterizing the sample complexity of verification, I think, is a really interesting open question. We have other results in this work, but I won't talk about them. The main thing I want to talk about today, especially because I'm at WoLA, is distribution testing tasks. Okay, so distribution testing without a prover. I assume everyone here knows and loves this task. So we have some underlying distribution over a discrete domain of size capital N. And we want to understand whether the distribution has a property. Okay, property is the same, just a subset of all the possible distributions. It plays the same role as a language for decision problems. So maybe the problem could be that the distribution is uniform over the domain. The property could be that the distribution has entropy. The property could be that the distribution is monotone in a sense that I'll talk about in a minute. So you know these kinds, or hopefully you know these kinds of problems well. And for distribution testing, our goal is to accept if the distribution is in the property, or a tester draws samples from the distribution and should accept if it's in the property and reject if it's far from the property. And I'll also talk about tolerant testing. So if you're excited about that, just wait a little bit and it'll come up in a few slides. Okay, so this is a very natural and well-studied, richly studied class of problems on data, problems about data analysis. And we can separate between label invariant properties, where there's been a lot of study. And label invariant properties are properties where if I permute the domain, the names of elements in the domain, membership in the property doesn't change. Okay, so for example, the property of being uniform over the domain is label invariant, right? If I relabel, if I relabel the ones as twos, I'm thinking about the support as being the actual numbers 1 through n. If I relabel 1 as 2 and 2 as 1, whether the distribution was uniform or not doesn't change. If it was uniform, it stays uniform. If it was not uniform or far from uniform, it stays far from uniform. Similarly, the Shannon entropy of a distribution, that's label invariant. The support size, the distance from the uniform distribution, all of these are label invariant properties. And we know that for tolerant or for approximate, for the search problems, for approximating these quantities, we know that the sample complexity of distribution testing is high. Okay, this is starting with the work of Sofia and Dana and Emil Spilka and Adam Smith. And the type bound was by Valiant and Valiant and over log n. So these are really hard problems. You need a linear number of samples in the domain size in order to decide them or to solve the tolerant versions of these problems. And we also have general properties beyond label invariant, and I'll get to those. I'll get to those later in the talk. So for these kinds of problems, for distribution testing, we want to study what happens with verification. Okay, so if some prover claims that the distribution is in the property, can we verify that more efficiently than we would need to decide it or to run a distribution tester in the standalone setting? What's the actual object we're after? An interactive proof for distribution properties. This definition is due to Chiesa. I don't know why, that should be Chiesa and Gur. I don't know why right? Yeah, I don't know what the S is. Okay, so we have an untrusted prover now that the prover enters, before we just had a tester that was drawing samples from the distribution. Now the untrusted prover enters the picture and we have a verifier. The prover claims that the distribution has a property. Completeness, we always want if the prover is telling the truth and follows the protocol, the verifier will accept with high probability. For soundness, if the distribution is far from the property, so this is the usual sense of farness, right? The distribution is far from any distribution in the property in total variation distance, then no matter what the prover does, the verifier should reject with high probability. Probability over coins it's allowed to toss and over the small number of samples it draws from the distribution. So this is what we want. And in terms of efficiency, we want, of course, the verifier's sample complexity to be small, so smaller than what's needed for distribution testing in the standalone setting. We want small communication, small number of rounds, small verifier runtime. Ideally, we'd want the prover to also be efficient. So we'd want the number of samples and the runtime of the prover to be close to what you would need just for distribution testing. But here you also get a proof. So not only can the prover decide the problem, it can also generate a proof that will convince the verifier. And we can talk about tolerant proof systems where we want to verify the distribution's distance from the property, or we have some close and far parameters. So completeness means that if the distribution is epsilon close to the problem, the verifier should accept. And soundness says that if it's epsilon far, then the verifier should reject with high probability. Okay, so we know that for label invariant properties, the complexity of deciding the problem on your own using a standalone distribution tester is almost linear in the domain size, but for verification, we can do much better. So we have this result for every label invariant property, almost every, has a tolerant, doubly efficient interactive proof, okay, many adjectives here. It's a protocol. It just has 2 messages. It's a private coin protocol, to your question. The first message is from the verifier to the prover. The second message is from the prover back to the verifier. The verifier runs in square root of n sample complexity time. Communication is square root of n. And the prover is almost as efficient. We said that just to decide the problem, you need n over log n samples, but you can generate a proof using a quasi-linear number of samples and running time.
Yeah. In quasi-linear, the prover could just learn the distribution. right?
Great question. So I want to say, so first of all, the prover can just learn the distribution, and it needs to learn the distribution in order to run in our protocol. Now, one thing that you may be getting at is that if I only wanted the sample complexity to be root n, that's all I was after, that I could do easily. The prover would learn the distribution. It would send over the complete description of the distribution, so something like n log n bits to the verifier, and the verifier would run a, what is it called, an identity tester or an identity tester using square root of n samples and verify. And this protocol was suggested by Chiesa and Gur. But the point is that the communication then is n is linear, and the verifier runtime is linear, and we want all of these to be sublinear. So all of these are square root of n.
Sorry, I missed. What's an identity protocol?
So the prover, in the protocol that was suggested, the prover is sending a complete description of the distribution that it learns. And the verifier, now all it needs to do is to check whether this complete description is really close to the distribution using a few samples.
So it's the size of the domain.
The communication is the size of the domain, but the sample complexity is small. So if all you cared about was sample complexity, you could do this. And this object that tests whether this like explicit description is close to the unknown distribution is called an identity tester. Okay, so right, so it's important we want all of these to be simultaneously sublinear to get a sublinear proof system, and that's a difficulty of getting such a result. Yeah.
Just existing from Delta, but then this big thing can be shrunk, right?
Yeah, so actually we have, so it can be shrunk. If you're willing to introduce cryptographic assumptions, then the sort of idea that you're outlining in your head can be made to work. So we actually have, I don't think we've posted it, but we have such a write-up. You have to put the things together carefully, but it does work. But that requires assuming collision-resistant hashing, and you'd only be sound against a polynomial time cheating prover. And you still get a protocol that has the sample complexity is still square root of n, but you can reduce the communication complexity if you're willing to make cryptographic assumptions and relax the soundness. Okay, so this works for every label invariant property. Tal is going to speak after me, and he'll tell you more about how you can actually, how this protocol actually works. I won't talk much about it. But it does apply to all the problems I was mentioning. So you can verify the Shannon entropy of a distribution, right? That's a pretty basic thing that, so now we have a protocol for doing that. Given an unknown, samples from an unknown distribution, you can verify its Shannon, what its Shannon entropy is, its support size, its distance from uniform, all of these properties. I also want to mention that the sample complexity is optimal. And by this, I mean it's optimal for any protocol, no matter how many communication rounds you have, how much communication is sent, what the honest prover runtime is. I want to, when I say prover time here, this is the running time of the honest prover generating the proof, but soundness is against any unbounded cheating prover. And the sample complexity is optimal even if you were allowed the honest prover to run an exponential time and exponential sample complexity, so it perfectly knows the distribution. You still can't get below square root of n sample complexity for verification. It's very interesting to ask whether you can get the communication to be smaller than square root of n. Okay, so as far as we know, it might be possible to even get polylog communication. The sample complexity can't be improved. And I said it was a private coin protocol. Okay, so that's what we knew. These are two results from the last 2 years. And I want to tell you what we know. So this is general in the sense that it's for any label invariant property. But of course, many, many interesting properties are not label invariant. And that's what I want to spend the rest of the talk talking about. So any questions about this before I move?
So we assume that the domain is n and we narrate and everything is expressed in terms of n, but I mean, there could be scenarios where like n is actually just like exponential in dimensions, right? You actually care about something much smaller. Like, oh, I promise you that it's actually just like succinct in some sense. Can you somehow get the dependence on like the true thing?
So I'll tell you about a result where the dependence is on the support size, the actual support size, if you have a promise on it. So I will tell you about such a result, then you can stop me and ask me more. Here at this point, I don't really know how to think about it because then it immediately becomes not label invariant, right? So.
Oh, I mean, you could be, I promise you that it is uniform on some subset of the domain, like there was a paper with Tucan on that kind of thing, that you don't even have a promise on on the full domain. That could be all integers, but I promise you that there is a small subset maybe on which you're uniform.
So I think for, I mean, we should probably take it offline, but I'm going to guess that you could hash the domain size down and run this protocol on the hash domain. And it's just a question of whether you can translate label invariant properties on the hash domain to the original thing you were interested in. So that's a kind of, that's my conjecture, but I don't, yeah, I don't know. Okay, good. So this is for label invariant, but now I want to tell you about moving beyond label invariant properties. So it's interesting for me. For me, it was immediately clear that like, oh, I want to go beyond label invariant. But then, Tal kept asking me, I didn't say this is all joint work with Tal Hellman, who'll speak after me. Sorry, Tal. So I was like, no, we have to go beyond label invariant. That's super interesting. And Tal kept asking me, okay, but what's not label invariant? And I was like, I don't know, but I'm sure like everything has to be not label invariant. There have to be lots of interesting non-label invariant properties. Of course, it's true, but like what's been studied? So I really like this example of a monotone, the property of the distribution being monotone, which was studied in several works by Ronit and co-authors. So what's a monotone distribution? Or this is the property I want to focus on as an example, running example for the rest of the talk. So a distribution is monotone. We have some partially ordered, we have some relation, partial ordering over the strings in the support. Say this is over the Boolean hypercube. Okay, so the domain is of size capital N, which is 2 to the little n, and it's Boolean strings of length n. And a distribution is monotone if whenever two strings, so the partial ordering is x is larger than a string x is larger than x prime. If everywhere where x prime has a 1, x also has a 1. Okay, so it's monotone in that sense. You can't flip any ones to zeros. Okay, all the places that are 1 here or in x prime are also 1 in x. So if that's the case, then x must have larger probability than x prime. Okay, so if this is satisfied, then the distribution is monotone. And now we can ask, and it's kind of, if you think about a distribution where, I don't know, we have some, these are features and they're correlated with what we expect people's probabilities to be. Like, I don't know, like the more you have features that indicate you're wealthy, the higher your probability in the underlying distribution. It's a natural kind of property we expect in some settings for a distribution to have, and we'd like to know whether the distribution satisfies this property. So it's really nice, and this is fun to think about. Unfortunately, here also, Ronit, who's the V? Vasilian, thank you. Showed that the sample complexity also is almost linear in N for distribution testing. Am I correct? I'm super worried that I'm going to make a mistake when I'm good. Yes.
But it has a Mariam Aliakbarpour and Temes Kouliakis, John Peebles, and Anna Chiapignani. And I know I'm forgetting somebody, so.
It's my fault, not your fault. Okay, so anyway, take this tightness with a grain of salt, but we need an almost linear number of samples in order to test for monotonicity. For the talk today, I want to talk about a simplification. I don't know if the simplification is still hard, but it'll be helpful for us. Okay, so we have a promise that the distribution is uniform over half the domain. And we have both in the yes case and in the no case. This is a promise, but we want to understand whether it's monotone or far from monotone. Okay, and now we get to the visual arts part of the talk where I've tried to draw a monotone distribution. Okay, so this is again the Apple approved drawing of a distribution. And this is my postmodern impression of the Boolean hypercube over 4, n equals 4. Okay, so this is the all 0 string. This is the all 1 string. And here we have the strings of Hamming weight 3, Hamming weight 2, Hamming weight 1. Okay? And here we have a distribution. The blue elements are the ones that are in the support, and it's uniform over its support, and the white elements are not in the support. So is this monotone or not monotone? It is. Okay, someone understood the drawing or guessed, right? So all the strings, the strings here are all, for every string here that's a 1, all the ones that are below it, according to the relation, have 0 weight. Okay, every string here that's in the support, all the strings that are smaller than it are not in the support, and all the strings that are above it, according to this to the ordering, are in the support. So it's a monotone distribution. I'm pretty sure. Okay. And here we have another distribution, and this one I believe is far from monotone. Okay, so like there's weight here on the low Hamming weight elements and on the high Hamming weight elements, but there's no mass in the middle, so this is far from monotone. Okay. So I want to have a verification for the property of, is a distribution monotone, but I actually want to be more general, and I want to be the most general that I can. Now, when I talk about properties that are not label invariant. So how general can I be? This is more or less the limits of my imagination. What I want, somehow deciding membership in the property has to be, membership in the property has to be decidable, right? I don't want it to be something like the distribution is describing the halting problem, is it in the property or not? And I don't want it to require exponential time to decide if the distribution is in the property or not. What I want is that given an explicit description of the distribution, so if someone actually tells me this is the distribution, this is the probability of the first element of the, the all zero string, and this vector, and this vector, and this vector, and someone actually writes down for me the 2 to the little n, or like n size table specifying the probability of every single element in the distribution, then I should be able to decide if the distribution is in the property or not. Okay, so that's just a purely computational problem. There's no sample complexity issue here. I want all the properties. We're given an explicit description of the distribution, just telling me what all the probabilities are up to some rounding error, up to some precision. I can decide whether the distribution is in the property or not. Okay, so that's my kind of most general notion of what kinds of distributions I would shoot for. Okay, so I want to be able to verify membership in any such distribution property. We're not going to get all the way there, but almost. So what I want is distributions where we have what we call an approximate decision procedure. So we have a Turing machine or a circuit that's a polynomial size that gets the complete description of the distribution. Again, the complete description is just a string. It's of length larger than n, and outputs the approximate distance of the distribution from the property. So now I want to talk about any distribution that has such an approximate decision procedure. It's a computational characterization of the property. Okay, distribution testing can still be very, very hard. Right? This is a purely computational problem. If we want to think about the property of being monotone, if I get an explicit description of the Boolean strings and the probability of each one, then I can just sort that description and check that for every pair where there's an x larger than x prime, the probability of x is larger than the probability of x prime. Okay, so if I do check all of these pairwise comparisons, that's an n squared time Turing machine, and I can do it. So I have an approximate decision procedure, at least for deciding if it's in the property or not, but I can also approximate the distance from the property.
So why do you say distribution testing can still be hard? Because, tester could always also get the explicit description after rounding error.
Using n samples. So it can be, when I say it's hard, I mean it can require a linear number of samples. Yeah, that's what I mean when I say hard. Yeah.
So the problem, approximate decision, is it clearly easier? It could be harder.
Harder than what?
In deciding whether, one thing is to decide if it has a property, another thing is to actually give the distance.
That's true. So we need, or I assume that we can give the distance.
You assume it, okay.
I assume it. I think if we just wanted, because I want a tolerant verification procedure, so I need to be able to distinguish whether it's epsilon 1 close or epsilon 2 far. I think if I just had, a procedure that decided whether it was in the property or far from the property, I think I could still get a proof system, but not a tolerant one. I'm not sure about this, but I think it's true. So you're right that we're assuming something a little bit stronger in the sense that we can approximate. The computational problem of approximating the distance has to be tractable.
Sorry, one more question. When you say complete description, the problem is technically a probability. It's like a real number, and so there's rounding. And so shouldn't you only care about I don't know, maybe log n bits of precision or something like that?
I do. Yeah, I'm lying. So I do only care about log n bits of precision and all the, yeah. And if you wanted polylog, fine, but I don't see why I would ever care about polylog. Yeah. So the description is of length n log n. Okay, good. So this is, the most general thing that I would like to shoot for. What we get, okay, so once we're talking about this as a computational problem, maybe we can talk about properties, not the whole class of properties that has, polynomial time decision procedures. We can talk about the ones that run in bounded depth, say the ones that have circuits of polylog depth, like NC, or even linear depth, or we can talk about the subclass that has Turing machines that don't just run in polynomial time, but run in polynomial time with polylog space or some small polynomial space. And this is the collection of properties for which we will show an efficient verification protocol. Always when I haven't given this talk a million times. This is the second time, but I've given informal descriptions. People always get confused about the fact that there is a problem, a sampling problem, the distribution testing problem, where you just have samples from the underlying distribution. But we're talking about, so that's a problem we want to solve, but the properties we want to talk about, the properties for which we want to solve the problem, are characterized by this computational procedure, that gets a description of the distribution and decides if it's close or far from the property. Okay, so this is a very, very general collection of properties. And I think one of the distinctions when we go from distribution testing or the property testing world, usually we think about problems when we don't have sublinear testers for every string property or every distribution property. We have to really think about the property we have at hand, and usually it has some combinatorial structure or some algebraic structure, and we can design a tester for it. When we're talking about verification, the situation is different. We have whole collections of problems that are just characterized by their computational complexity, and we can still get protocols. So that's kind of like a qualitative difference once we talk about verification. So this is our result. It's going to be in the upcoming Fox, again with Tal Herman. Every property that has an approximate decision procedure that can be implemented in bounded depth or bounded space, think of these as polylog, although they can be a small polynomial, has a tolerant, doubly efficient proof system for distribution testing. The verifier sample complexity and communication are no longer square root of n, unfortunately, but they're bounded away from 1, so it's like n to the 0.95. Probably this can be improved. The prover runs in polynomial time and almost linear sample complexity. N is a bound on the distributions domain, but going back to Clement's question, more generally, this can be a promised upper bound on the support size of the distribution.
How much can you reduce if you are willing to get on the computational service? In the communication, I guess, can be shrunk.
You can get to using cryptographic assumptions. You can get all the way to square root of n.
Communication, also can you also say
communication complexity can be polylog or security parameter, and sample complexity square root of n.
Get management separate for this.
Yeah, right. Tal, I'm not. Yeah.
Let's do something. I know it hasn't been asked in this context. If you have two provers, okay, so there would be some way to check consistency of the answer to something. Could you maybe hope to reduce the verifier?
Can you repeat?
So yeah, so Shafi's question was, if you're willing to give me one prover, why can't I have two? And if we have,
we're trying to argue that this is going to be something that might be useful, this verifiable data science. So
totally
reasonable.
Totally reasonable.
Reduces the verifier.
Totally reasonable. So we have two provers who we assume are not colluding. And how does the situation change?
The question is, what it is they were doing. In this protocol. Because if a lot of it is checking.
So I think that my suspicion, I don't know. I remember thinking about this for the label invariant case, and there I didn't see how it would help. But I haven't thought about it for the general case. And it's not exactly the same. The things Ron is asking about with relaxing to a computational model and computational security. Usually in the world of crypto, we know through Killian's protocol that basically what happens is we take a two-prover protocol and we can run it with one prover using hashing or whatever, using commitments. I don't know if that's the case, if that would still be the case here. So I'm not sure. I don't want to answer I mean, it may be that I think about it for 5 minutes later. I tell you that in that model you can do much better for this, or it may be that not. I'm not sure, so I don't know.
For example, even to know that.
But the model makes total sense.
Yeah. For example, even to check that this is a probability distribution in the most basic sense, that the probabilities add up to 1. That's consistent. Smells like consistent. Because I don't know. I mean, you're assuming that, right?
I mean, I haven't told you anything about what I mean. What does it mean? Like, it's not that the prover is committing to some distribution and you're checking its consistency. I don't know. I haven't told you anything about what's happening inside this protocol. But you're on the right track. This is the kind of thing that you want to verify if you have two provers. Maybe one of them is an oracle where you give it I and it tells you the probability of I, and with the other one you want to check that this is somehow consistent. But anyway, let's take it offline because I think we're going into. I think the model makes total sense. And then there's a question of what you can do with it and what you can save. Yeah.
So I guess I've got the exact opposite question. What if you have one prover, as a big data set or whatever, but many people that ask independently kind of similar questions or even the same question? Can you reuse the computation? Do you need to keep taking samples and all that?
So I think in all of our protocols, the big step that the prover does, as was kind of hinted at in various questions, is to draw enough samples to learn the distribution. And it builds a big table for itself that tells it for every element what the probability is. And as you'll see in Tal's lecture, one of the basic things it does is you send it the index of an element and it should respond with a probability, and you want to check that its responses sort of are close to the underlying distribution. So this work of building the table just has to be done once. Yeah, but I don't know. I mean, also, yeah, if you can have a but if they're asking different, anyway, if you just want to make it non-interactive, you can't use the Fiat Shamir because it's not a public coin protocol, but Tal has a public coin protocol that you could use. And if different people are asking different questions, I don't know. Yeah. Okay, good questions about the model. Okay, so I want to tell you, in the time I have left, I just want to tell you a little bit about this result and how we prove such a thing. And to do that, I have to do a brief detour because I guess we haven't had enough models in the talk so far. I want to briefly talk about interactive proofs of proximity for string languages, which is a main component in our proof. Okay, so one of the main tools we use is an interactive proof of proximity for string languages. Okay, so here we have an input that's a string. Confusingly now, it's a capital N length string, not like the strings in the support of the monotone distribution. And we want to verify whether it's in a language. Okay, similar to a property, there's some language. Is this, does this string describe a bipartite graph, or I don't know, some language that we want to verify. And we want to verify in sublinear time. So the verifier has query access to the string. It should query a few bits and then accept or reject. And we want the usual kind of property testing guarantee where if the input is far from the language, then no matter how the cheating prover, no matter what strategy a cheating prover follows, the verifier should reject with high probability. Okay. And this was introduced in a work of Rugun, Kumar, and Rubinfeld. This model, it wasn't called proofs of proximity there. And yeah, and we want everything to be sublinear. So the query complexity, the verifier runtime, and the communication should all be sublinear. The reason I want to tell you about this model is that here we have very powerful protocols, or very general purpose protocols. Okay, so this is work with Salil Vatan and Avi Vigdersen. The result I'm telling you is in work with Ron Rothblum, that every language, string language, decidable in using bounded depth circuits of polynomial size or bounded space Turing machine, has an interactive proof of proximity with sublinear queries and communication. Okay, the square root of n, I'm telling you because that's the bound, that's kind of the state of the art bound, and probably also optimal under assumptions. But anyway, the main point is that we have, for general languages on strings, we have sublinear proof systems for string languages. And I want to use that. That's the main idea. I want to use that. I want to use these results in order to get proof systems for general distribution properties. Okay? So we want to design an interactive proof for distribution property, okay, where the verifier can sample from the distribution. We want to verify, that the distribution is not far from a property. And here we said we only had protocols for label invariant properties. We want to go beyond that. What we want to use is proofs of proximity for string languages. Okay, so here the verifier has query access to a string. Okay, we want to verify that we're not far in Hamming distance from a language. Okay, so the language and the property are playing analogous roles. Here the distance measure is Hamming distance. Here it's total variation distance. Okay. And here the main advantage here, or what we want to use, is that we have protocols for general languages. Okay, for anything computable in bounded space or bounded depth. And the main idea, as I've hinted, is to have a reduction. Okay, to given a property over here, when we want to design an interactive proof to verify membership or distance from the property, we want to reduce that to building an interactive proof of proximity for a string language. Okay. So let's go back to our example of monotonicity. Okay, so we have a distribution. To make, we won't, if we want to do the general case, we won't leave here. We won't leave. So we have a promise that the distribution is uniform over half the domain. We're going to use that quite extensively. And we want to verify that it's monotone. Okay. So I'm going to reduce to a string language. And the way I want to build a string that describes this distribution. And the string is just going to have ones in the elements that are in the support of the distribution and 0 in the elements that are not. So half the elements in the string are 0, half the locations in the string are 0, half of them are 1. And this describes which elements are in the distribution support. Okay. We want to verify that the distribution is monotone, and that translates naturally to a language over strings, right? Like you sort the elements, and you see that kind of for any 2 elements, if one of them is in the support, then the one that's larger than it is also in the support. The main point is that we can translate from a property, distribution property here, to a language over the strings that are describing the distribution. The strings are very simple, just which elements are in the support of the distribution and which are not. And we can also translate statistical distance of the distribution from the property to Hamming distance of the string that we've built from the language. This you'll have to believe me. Because it's uniform, yes. So we're really leveraging, okay, I want to warning, we're really leveraging this simplifying assumption, and it really is a big assumption, but this way we'll be able to get some glimpse of the idea. Uh-huh. No. So there are many strings. So for any monotone distribution, there's a string that describes it. And that string is in the language. Yes. Sorry, we're on the hypercube throughout. I know, yeah. I don't quite have it in my head that there are also other settings where it's also been studied on the integers. Yeah, but we're on the hypercube. Okay, so we've built a string, we have a language, and we have a protocol. So let's just run it. Okay, so this protocol will need, the verifier will need query access to the string that we've built. And this is the catch, right? We do not have that, right? We've built this string. We're imagining it. We've built it, or we can imagine it. Given a distribution, the string is well defined. But we can't query it, right? Why not? The only access we have, all we can really do is draw elements inside the support of this distribution, right? We can just sample from this distribution. That's all we have. So what is that? Sorry. Okay, ignore this. I'll talk about it in a minute. But all we can do is sample ones in the string, right? We can sample elements from the support of the distribution, and that translates to having a uniformly random element in the string that's 1. We certainly can't query it, and we cannot sample outside the ones. We can't sample from the zeros. Okay, so that's the problem. I want to say the proof systems here don't actually, query access sounds really scary. Like you would need to be able, given an element, to say whether it's in the support or outside of the support, and we just can't do that. You need something a little bit weaker. So really the way this protocol is built, you have an interaction phase between the verifier and the prover. And after the interaction, the verifier chooses a random set. So it's one-wise random at the very least. So each query here, even given the whole interaction, its queries are one-wise uniform. So it's really choosing a random place that it looks at and some other places for consistency. Okay? But you do need to be able to, at the very least, you need to also be able to query places that are 0. Even if it's a random place, you do need to be able to query the zeros, and we just can't do that. Okay. 5 minutes. Okay. So let me just tell you briefly how we get around this, or how the protocol actually works. So we have this reduction. Given the distribution, the string that we're interested in is well defined. We can run the interactive proof of proximity during the interaction between the prover and the verifier. The verifier never needs to query the string, so that we can do. At the end of the interaction, the verifier needs to draw some random indices for which it needs to know whether they're zeros or ones. Are these elements in the support of the distribution or outside the support of the distribution? So we can do the interaction, but we can't query, right? All we can do is sample from this distribution. So that's what we'll do. The verifier draws one sample and actually chooses the query set in a planted way. This sample that it shows is planted inside the query set. And it can do this while preserving soundness because the query set is random enough. Okay, so you'll have to believe me. So the verifier takes a random sample from the distribution. That's a random place that should be a 1. And it chooses the query set to include this sample. And now it just asks the prover. It sends the query set to the untrusted prover and asks it, OK, what are the values of the string in these locations? Okay, for each of these locations, is it a 0 or a 1? Okay, what's the untrusted prover going to do? It's going to lie, right? It's going to send some values that make the verifier accept. Okay? And all that the verifier can do is it has one location where it knows that this should be a 1. So it checks that. It checks the prover's answers. It checks that in the location that was planted, the actual answer is a 1. And that the prover made the string verifier accept. Okay? So now when the prover is cheating, okay, if it actually sends back the correct values of the string, the verifier will reject. Right? That's the soundness of the proof system for the string. So it needs to cheat. It needs to flip at least one of the bits from 0 to 1 to get the verifier to accept. If it flips a 1 to a 0, it might be caught, right? Because this might be the place where the planted place where the verifier knows it should be a 1. And then the verifier will reject. So what it'll do, it'll flip zeros to ones. That the verifier can't check. So it has this kind of one-sided freedom. It can flip zeros to ones as much as it wants, and we won't catch it. But if it does that too much, we know, since the queries are more or less random, and we know that half of the indices were 0 and half are 1, if it changes too many zeros to ones, we'll be able to detect that. So the verifier also needs to check that in the answers, the number of ones that it's seeing is about what it should be. Okay, so it should be q over 2 plus or minus the size of the query set. And what I don't have time to show you, because I ran out of time, is that this is actually enough. So what we need is we build the proof system, the underlying proof system for the strings, so that the prover has to cheat in many locations, not just one. And now if it flips many ones to zeros, we'll catch it with high probability. That's an amplification. If it flips many zeros to ones, it won't, that's too many, and we'll see that there are too many ones, and we'll reject. So that's essentially, that's the idea behind the protocol. I really, really relied on the fact that we knew that the distribution was uniform over a set of size n over 2. I didn't know which one. So for every element that I sampled, I knew that its probability was exactly 2 over n. And that was important. It was used, if I talk about a general distribution, it's not clear how to build a string that represents it. It's not clear, how do you know if things are 0 or 1. So things get much more complicated. The main thing I want to tell you about the general result is, first of all, if I was able to sample elements together with their probabilities, if I had such a sampling procedure, then things would be pretty simple. I mean, you still need to you need to generalize this reduction using hashing, but you can do it. So this is really the key thing. The verifier needs to be able to verifiably get samples that have, samples from the distribution together with their probability. What we use in order to do that is a verified tagged sample protocol that appeared in our previous work. Okay, so we can get a collection of samples, and that's what Tal will talk about in his talk. We can get samples together with approximately correct probabilities. And this approximate correctness is a real pain that you need to deal with. The probabilities are not perfect. The prover can lie by a little bit. Mainly, its goal in the protocol is to downgrade the probabilities of elements, because that turns ones into zeros, and that helps it. So there's a lot of work that goes into dealing with errors in the tagging. And you can ask us about that in the poster session or in the break. So that's the result we get in the end. And I'll end here. So we saw that we have this high-level goal of verifiable data science via proof systems. We have protocols for agnostic learning. for label invariant distribution properties, and now also for general distribution properties. I'm sure the constant we have here in the exponent is not optimal. And I think it's a great open question to ask whether you can get this all. I mean, okay, so first of all, improving the constant would be nice. But can you get it for general distribution properties all the way down to square root of n? My kind of very I don't know, based on nothing intuition is that maybe the correct answer is something like n to the 2/3. This is a more challenging setting, but I don't know. I'd be delighted to be surprised and and see protocols with square root of n samples for general properties. And I think I told you about some specific results. There are tons of questions here, so I think really, I hope more people are excited by this. By this area, because there are many more questions than we have answers. So every time I've given this talk in the past, Shafi asked a question which she did not ask today, so I'll say it. That here I focused on the regime where the properties are already so hard to test that kind of going beyond a linear number of samples in the domain is progress. So that's great. I mean, the fact that we can, for such challenging properties, we can get efficient verification is great. But it sort of also lets me off the hook easily, because then I can tell you that even if the prover runs in linear time in the domain size, that's interesting, because I mean, solving the problem requires an almost linear number of samples. There are many properties, if we're talking about, for example, verifying machine learning, we really want the sample complexity in the standalone setting is not, the domain is huge. The domain we can think of as being exponential. So we want the tester to run in polylog time, and then I'd also want to be able to generate a proof in polylog time. So in general, this question of the relationship between the sample complexity of testing, verifying should be more efficient than testing, and ideally proving should not be much more than testing. So if testing is already strongly sublinear provers are interesting. Talking about high-dimensional data, I think, is very interesting. And this is super speculative, but going beyond verifying just distribution properties, if we have any setting where we want to verify correctness, so I don't know, maybe we have a language model that's hallucinating or fake news. So you can, in such a setting, you need to think about what kind of access, what is the truth? What kind of access does the verifier have to the truth? And can you get protocols where verifying requires less expensive access to the truth than you would need in order to run the analysis? So I think you can come up with some very general questions. OK, and I'll end here. Thank you.
Is there any question for Guy?
Yeah, quick question related to the first frontier, I guess. So if I insist that the prover do not learn the distribution, so even slightly sublinear suffices, can I get any lower bound on the verifier or communication, or?
Lower bound or upper bound, and for what properties? So we have properties, we do have examples of properties where the prover can be sublinear. For example, the agnostic learning result I told you about can be phrased as a property testing setting. And the prover there requires VC dimension many samples, and the verifier is square root of VC dimension. But understanding this in full generality, I think, is very interesting. So we have examples where it's possible. Can we come up with more? Or can we characterize when it isn't and isn't, when it is and isn't possible? No. So we have examples where it's not possible regardless of the prover sample complexity. But I don't have an example where it's specifically about the prover sample complexity.
I actually have two questions. But so the first one is, so I realized that square root n samples is necessary. There is a lower bound, as you mentioned, but that feels really, I'm really unhappy about this. So I was wondering if you could think of a setting, maybe giving a tiny bit more power to the verifier to break that square root n thing, because.
So we have natural properties where you can break it, specific natural properties where verification is polylog, or even less, even constant number of samples. So there's a huge gap. The square root shows up again and again in different results. So I don't know. I think there may be a lower bound, or it's something to think about. I mean, it's not that, verification can be, can improve things by more than square root. So we have specific examples where you can go more than square root. So you won't be able to show a lower bound saying that you can never improve more than square root for verification. But it does seem to show up again and again for interesting things, for things we're interested in. So I don't know. My feeling is that there's some barrier there, but maybe I'm wrong, and everything can be, and there are many, many super interesting properties where you can do less than square root.
And maybe the last one is, so my understanding of the protocol is at the end, the verifier learns a lot about the underlying distribution, not just one question about the properties they want, but like actually a histogram. If I want to put like zero knowledge in the picture, etc., have you thought about that?
So we have general reductions in crypto that say if you have a protocol, you can transform it to be zero knowledge, where the prover, instead of sending anything in the clear, it sends it under an encryption, and then it proves that if it opened the encryption, you would accept using a standard zero knowledge proof. So you can build such compilers using crypto. Maybe it's interesting to ask, can you do it without crypto? So if we want to talk about statistical zero knowledge, what's possible? And I have no idea. I think that's an interesting question. Or under minimal cryptographic assumptions, like only the existence of one-way functions. I'm not sure that you can get, well, also given Tao's public coin stuff, that would allow you using only one-way functions. So anyway, I think there are some interesting questions, but if your question is, could you imagine that you can do this in zero knowledge? Yes, you can do anything in zero knowledge. Just put everything under an encryption and then prove. No. So the gap between the honest prover and the verifier is in sample access, but the dishonest prover can run, also has much more running time. And
You gave the verifier the running time too, and just said the gap between the prover.
So sure. So the zero knowledge will be against polynomial time parties, and if you wanted statistical zero knowledge, which is unconditional, then I don't know what you would do. That was
Thank you. Yeah. So, while Tal is setting up, let's thank Guy again. And